Hey class, let me go back. I'm gonna make videos for these slides, but I made a mistake today. I said something wrong. I said that the cofactor, I gave the definition of the cofactor incorrectly. So the cofactor, it's that sign that I did find, and it's the determinant of the minor or the submatrix. But I also said that the cofactor included the entry, like Aij, and that was incorrect. So it's Aij times the cofactor that you would add up when you do cofactor expansion. But that was my mistake. I defined that wrong for you guys. So it doesn't include Aij. So, for example, the cofactor C11, the cofactor, let's pick a better one. C1, first row, second column. So here 2. So I said that 2 would be involved in it, and that's not true. It's just a minus 1 to the ij, to the I plus j, which is odd. So it's going to be a minus 1. So that I plus j is going to be 1 plus 2, so it's going to be 3. So minus 1 times the minor 4, 6, 7, 10. The determinant of that minor 4, 6, 7, 10. And so that'll be 40 minus 42. So a minus 1 times that, so that gets a minus 2 times a minus 1, that gets us 2. So 2 is the cofactor. I notice I didn't multiply that 2 times this yet. So that, I apologize, but I was teaching you guys incorrectly. So here you can see that the Aij times the cofactor is what you end up adding all up. So we can jump back again. So these are some things we touched on in both classes, but quickly, if one of the rows or columns is 0, then the determinant of A is 0. If A has 2 rows or columns that are the same, then the determinant of A is 0. And this you can extend, so if one row or column is a linear combination of another one, or a scalar multiple of another one, then the determinant of A is 0. And if one row or column is a linear combination of the other ones, then the determinant of A is 0. So if a multiple of one row is added to another row to produce a matrix B, then the determinant of B is the same as the determinant of A. That does not change the determinant. If 2 rows of A are interchanged to produce B, then it changes the sign of the determinant. And if one row of A is multiplied by K to produce B, then you can get determinant of B by multiplying the determinant of A, which is your old matrix, by K. So those three, we did get to all of those in class, in both classes, but just a quick review. We will use those more later on in this video and in class tomorrow. So find the determinant of this. So we could use our special way to do 3 by 3 or cofactor expansion, but once you know how these row reductions impact the determinant, then it makes it easy. These also come into play because if you're doing row reduction and you end up with a row or column of zeros or 2 rows that are the same, then you don't have to go any further. So here's the matrix. Begin by swapping 2 rows. What happens? Well, if I swap 2 rows, I've got to change the sign. And then, so if you multiply by 1/4, then you've decreased, or multiplied by a negative 1/4, that first row, then that means you've decreased the matrix. This will be a minus 1/4 less than the original, so you have to multiply it by a minus 4 to keep the determinant the same. And then right down here, we took a -3 times row 1 and added it to row 3. And that does not change it at all. And then we took 2 times row 2 and added it to row 3. Doesn't change it at all. And now we're at a triangular matrix. So multiply the 4 times the 4 out front times the 1 times the 1 times the -3. You get a -12. So pretty slick. It can save us a lot of calculations, especially the larger the matrices. So here's another example. You can try, just for fun, do that by cofactor expansion to find the determinant of the matrix, and it'll be pretty crazy. So you can start, we've got a 1 here, so let's put that up top, and that's going to change this. So we're going to swap the top and the bottom rows. That's going to change the sign. And then we can do all of those row operations to all of the multiply row 1 by something and add it below. They're not going to change. So we can multiply by a -3, add it to row 2 to make that second term a 0. Multiply by, or just add the first row to the third row, and we'll get the next one 0. None of those change the determinant. But now we want this term to be a 1, so we're going to multiply by 1/12, but that's going to change the determinant of the new matrix. It's going to be 1/12 the size, so we have to multiply by 12 here. So you can think about it as pulling out a 12. So out of a row, we pulled out that 12. And then we can do row operations again to get these next two 0. Those don't change anything. And then you can do, this is already a 1, so you don't have to do anything there. And then you can do one more row operation where you're just adding that third row to that fourth row to get that to be 0. And you're at a triangular matrix, multiply by. A lot faster to do that. Well, still, I don't know if it's a lot faster with a 4x4, but still slicker. Okay, so we are, I think I emphasized this in both classes, at least a little, but just to emphasize it again, a square matrix A is invertible if and only if the determinant of A equals 0. So that means that if the determinant of A equals 0, that's another thing we can add to our long list of things that are equivalent to having an invertible matrix. It's like the columns of A are linearly dependent, the rows of A are linearly dependent. So those are the same thing as the determinant of equaling 0. Determinant of A doesn't equal 0 means the columns of A span Rn and the rows of A span Rn. So all of those things, all of the determinant isn't 0, we know all of those. We know it's not invertible, and if the determinant of A is not 0, then if the determinant of A is not 0, then we know it is invertible, and we get all of those other things from the invertible matrix theorem about the spans and the columns and everything else. So compute this. Well, it says it's 0. Why is it 0? Well, by inspection, if you add the first two rows, you get the third row. So it's not an invertible matrix, so the determinant is 0. The determinant of A transpose is the determinant of A. So why would this be true? I don't like the way that they prove it in this slide, or in the next couple slides. I'm going to try to prove it in class next time using elementary matrices. But you might start to convince yourself that it's true just by trying an example. 1, 2, 3, 4, 5, 5, 6, 7, 8. And the transpose would be 1, 2, 3, 4, 5, 5, 6, 7, 8. So this, well, to begin with, you can think, well, if I'm going to I can pick a row or a column to expand along. So if I can pick this row to expand on, and then I can pick this column to expand on, and so and do cofactor, and so then you can do you get 1, 2, 1 minus 2 times its minor plus 3 times its minor. And are the minors going to be the same? If I eliminate the row and column with the 1 over here, I get 5, 5, 7, 8. Or over here, I get 5, 5, 7, 8. 1 minus 2 times its minor plus 3 times its minor. And they aren't the same, but again, since you can pick whatever row or column any row or column to expand on, just pick the 5, 5 one. Here, pick the 5, 5 one, and just expand. Although we don't usually do that with 2 by 2s, but the transpose of a 2 by 2 is the determinant's the same because the diagonals stay the same, and it just changes the off diagonals. So you're still going to get 5, 8 minus 5, 7 either way. So it's true for 2 by 2s. But in general, you could just pick, I'm going to pick the row here, the column here to expand on. I'm going to pick the row here to expand on as I keep on going. And then 2, eliminate the row and the column. I get 4, 5, 6, 8. And up here it would be 4, 5, 6, 8. 4, 5 is the first column. So you just pick the first column here to expand on, the first row here to expand on. Oops, I said that the right way. And so you can see as you go through, if you just keep expanding along the same row or column, because the row in one is the column on the other one, and it doesn't matter what we pick. When we do cofactor expansion, whichever row or column, then you can just keep picking the same one, and you're going to end up with the same computations. So that's one way to think about that. So the determinant of A transpose, same as A. This is more of the proof that they do. Okay, this is called the product property of determinants. So if you have two matrices multiplied together, then the determinant of AB, then the determinant of that product, that's the same as the determinant of A times the determinant of B. It's not true for addition in general, so don't think it should be. So be careful. Like A and B could both be invertible matrices, but when you add them up, they could just be the opposites of each other, and you add them up, then you get 0. So, that's an easy proof there, but they do another example down here to show that it's not the case. We've already been almost using this. Well, one way to use this is as we were row reducing, instead of using the other properties of row reduction, we could think about it as elementary matrices, and we're building elementary matrices times something to eventually get down to the identity, and then the determinant of all these is just the determinant of each one, and that's kind of what we were doing back here in these examples. Like this is the stuff out front is the determinant of the elementary matrices that we could multiply by to get to change this back to the original matrix. So we've kind of been already using those, or we can make sense of this by using those two. All right, what about the determinant of A inverse? This claims that it's 1 over the determinant of A. This I did mention in class, because if you interpret this, if you interpret determinants as the area that's transformed, how much the area is transformed by a unit square, maybe you do this, and maybe the determinant is 10. Well, if that's what happens when you multiply by A, then when you multiply by A inverse, it has to take something that it's the area of 10 and get it back to the area of 1. So the determinant of A inverse better be 1/10 to get the area back to 1 if it undoes everything. So that's kind of the intuitive idea there. But here we can use the product property that we just learned, that the determinant of A times the determinant of B is determinant of A times B. Well, you can start by A times A inverse is I, take the determinant of both sides, and then use the product property to separate that out. The determinant of I is 1, so then you can the determinants are just numbers, so you can do the algebra with the numbers. You divide both sides by the determinant of A, you get that it's 1 over that. So here is the kind of problem that mathematicians make up to test to see if you really know how to know your properties and how to apply them. So sometimes, these actually can come up in practice. They're just usually way down the road. So, but the determinant of an expression, the rules that we have now can help us simplify that. What about the determinant of 2 times something? We have to know the size of the matrix. If we multiply, I don't know if we ever talked about this. Then that'd be from the book. If you multiply a whole matrix, if you multiply the whole matrix by a number, then it changes the determinant by 2 to that 2 to the power, where power is the number of rows or the number of columns in A. Easiest place to see that is if you have the identity matrix, etc. I don't know if I got the right number of zeros and all that. Yeah, anyway. I don't have enough. There, it's probably closer. 0, 0, 0, 0. Just pretend it's the identity matrix. If you multiply the whole thing by 2, then you get 2, 2, 2, 2, 2 down the diagonal, and so and it's a triangular matrix, so you multiply the whole thing by that. Take the products down there, you're going to end up with 2 to the 5th. So, but it actually doesn't matter what the matrix is, and you could make sense of taking, if you have a non-zero matrix, 1, 2, 3, 4, 5, 6, 7, 8, 9. If you find the determinant of this and it's multiplied by 2, then everything's multiplied by 2. So you get 2, 4, 6, 8, 10, 12, 14, 18, 16, 18. Then the determinant of this, well, if you pick one row to expand on, then you could factor out a 2. So it would be 2 times a 1, and then the 4, and then the 7. But then each of these cofactors, each of these minors, you could factor out another 2 on each row or column to get back to talk about the same minor as it was here, and you could just keep on going. So you'd have to do this one 3 times, and you'd have a 2, and then times another 2, and then times another 2. Okay, don't think that was the best explanation. So here this 2, since we know it's 5 by 5 matrix, we can pull out the 2 with to the 5th. Now we have 3 products, actually 4 products, but split it up into 3 if we want, or 4. He does it in 4, because A is A squared, and the determinant of all of that mess is the determinant of each of those things multiplied together. Determinant of A inverse is 1 over the determinant of B, and we have this down now to where everything's just A's and B's, and it tells us what the determinant of A is and the determinant of B is, so you just plug it in and evaluate. So, and that's it. So we'll talk more about properties tomorrow. There's some properties. We'll continue on. Thanks.